Welcome, my friends, to our discussion of the molecular interpretation of phase changes. Today we're going to be talking about what it means to stretch bonds in terms of the energy and also all the phases we went through and how energy relates to them on the molecular level. So today let's start by reviewing heating curve basics. So when we heated up a solid sample of water, we had this kind of curve. We had these weird two flat spots. Here, of course, we had ice during this phase, and this was the melting phase we found out. And here we had ice/water, and here we had just water, and here we had our boiling point. So this is when we started seeing the liquid boiling. And so then, of course, we had water/gas, steam maybe, and then over here we had just gas. So at this point, all the water was gone. We just had gas and it started shooting up again. All right, so as we talk about this, we're going to interpret on the molecular level just the main look of this graph. First of all, we need to explain why there are these flat parts here and here. It's weird that the temperature stays constant during the melting and boiling point. Even though we're constantly heating it, the temperature stays constant. Then also we're going to explain why. Notice here that this is a medium slope, which means it's kind of hard to heat ice. Notice here that it's a low slope, so it's a small slope, which means it is hard to heat. It takes a lot of energy to heat water. More energy than it does to heat ice, which is weird because it's still just H2O. So today we'll explain why it's harder to heat water than it is to heat ice. And then over here, notice how quickly the temperature rises for gas. That means that it's really easy to heat steam. So it takes very little energy to heat steam, whereas it takes a lot of energy to heat water and somewhat energy to heat ice. Today we'll understand all of those key concepts. Let's get to it. So first of all, when we talk about stretching of bonds, let's start with something that we have some familiarity with, which is a gravity analogy. So let's say you have a basketball in your hand, and of course there's this force of gravity between the basketball and the earth, pulling them both towards each other. This force operates just like the intermolecular forces between the water molecules. It's an attractive force that tends to pull them closer together. Now, when you throw the basketball into the air, this force of gravity tends to slow the basketball on the earth down, and it tends to turn those kinetic energy of the basketball as it goes up into gravitational energy. So it converts the kinetic energy, slows the basketball down, converting that energy into gravitational energy. This is a similar process with water molecules. As they go farther apart from each other, that energy, that speed, their speed is converted by the intermolecular forces into chemical energy. Talk about that in just a second. I'm going to move to the next slide, and if you need to pause, go ahead. Now, when a solid or liquid is heated, the molecules speed up in the solid. They collide harder with each other and push each other farther apart. Now, the consequence of this pushing each other farther apart is some of their kinetic energy is being converted into chemical energy. So as they go apart from each other, they slow down because they're attracted to each other. So they're being slowed down. And that energy now, just like before with the basketball, where it was stored as gravitational energy, except this time it stores something we call chemical energy. It's the energy in the bond between two things. So what that means is that when you heat a solid, some of the energy goes into speeding it up, but some of that speed then is converted into chemical energy as they push farther apart from each other. So it ends up taking more energy than you might expect to heat up a solid, because not only are you going to change the kinetic energy of the molecules, but you also have to stretch them farther apart. So those two things are having to happen, and both are using some of your energy. I'm going to move to the next slide. So you want to pause here, that's great. All right, comprehension check. Below are three liquids, and these three liquids, what I want you to do is rank them from weakest to strongest intermolecular forces. And then I want you to think about what does that mean in terms of the amount of energy it would take to heat them up. So go ahead and do that work now. Hit pause, and when you're ready to go again, hit play and we'll talk about the answers. All right, we're back. Let's do it. So when we look at the boiling point here, the boiling point for water is relatively high, which means the particles must really hold on really well together. Otherwise, they would break apart more easily. So water must have the strongest intermolecular forces. Now, acetone boils at a really low temperature of 56 degrees Celsius. That must mean that the molecules aren't holding on very well together and they break off fairly easily. So it has the lowest or the weakest intermolecular forces. So I'm going to put an A here for acetone. And then methanol is in the middle somewhere. So I'm going to put it right here in the middle, methanol. So we have acetone with the weakest, methanol, water. Now, when you heat a liquid or a solid, not only do you have to speed the molecules up, but you also have to stretch the bonds between them. So if there's a really strong bond, like in water, if the intermolecular forces are strong, it's going to be really hard to stretch them. So a lot of that kinetic energy that you put in, or that energy you put in, is going to be used to stretch the bonds. So it's going to be really hard to heat water. Now, acetone has these weak intermolecular forces, so it's going to be easy to stretch them. So acetone here and methanol here. Now, awesome. So we have the least energy. Acetone should heat up really easily. Methanol should be somewhere in the middle. And water is hard to heat up. It takes a lot of energy. All right, let's talk about melting now. So during the melting process, ice crystals break down, allowing water molecules to suddenly move around and they can fit closer together. Here's a great example of that. Here is ice. And you can see in this diagram, there's all these crystal structures. These water molecules are holding each other in place. They're trapping each other in place. And they open up these big gaps here in the middle with just empty space in between them. And these hexagon shapes are actually three-dimensional. There's another hexagon going into the board. There's one above here. So they're all in here, and there's all these open space in between them. Now, when ice melts, water, of course, ice floats in water, so it's less dense, and it's less dense because of these big gaps in here, these cavities. When it melts, the water molecules can fit closer together, and they can pack in better. But that does not mean their bonds are closer together. They actually, in order to do this breaking apart and moving around each other, requires a sudden and significant stretching in those bonds. So here, it's hard to tell exactly, but here, one of these bonds is like really close together. All these bonds are really close together inside this crystal. But in here, they're a little bit farther apart. And that stretching happens all of a sudden during the melting process, which means that during the melting process, all the energy you put in is going to stretch those bonds all of a sudden as they suddenly go from being trapped in place to moving around. And it's not a slow process over time, because either you're trapped in place or you're moving around. So it happens right away. And all that energy is being converted, you put in, into chemical energy in the water. All right. And this is why the temperature is constant during melting, because all the energy you put in is going into stretching the bonds, chemical energy, rather than kinetic energy, making them move faster. All right, we'll move to the next slide. So if you need to hit pause, go ahead. Now, it's important to note that during the melting process, we're just stretching the bonds. They're not being broken. They're not being fully broken. Sometimes you'll hear textbooks or other things say that you're breaking bonds when you melt. But in reality, what you're doing is just stretching those intermolecular forces. And that does convert energy from kinetic into chemical potential, but it doesn't fully break them. And this energy that's required to stretch the bonds during melting has a special name. It's called the enthalpy or heat of fusion. Now, this word enthalpy here is just a fancy pants way of saying the word heat. In AP chemistry, we'll learn how enthalpy and heat aren't exactly the same thing, but for now we can think of them as virtually the same thing here. So the enthalpy is just a fancy word for the word heat. So enthalpy of fusion. And the reason we use this word fusion is because when water gets frozen into ice, it's like it fuses and turns to a solid, right? So that's where that word comes from. So the enthalpy of fusion. And the energy it takes to melt ice or to freeze ice is the same in both directions, and or freeze water, I should say, and it's still called just the enthalpy or heat of fusion. I'm going to move to the next slide. Heating a liquid. So we notice from the graph that heating water requires more energy than heating ice does. And here's the reason why. As you heat a liquid, just like in ice, the molecules move faster, hit each other harder, and push farther apart. So some of the energy you dump in goes to kinetic energy, but some goes into stretching those bonds, just like in ice. Now, in addition, water can do some things that ice can't do. Namely, the water molecules don't just sit and vibrate, they're moving, and they can actually rotate. So any energy that you dump into the system goes into three places. It goes into the kinetic energy, making it move faster, and that we're going to measure as an increase in temperature. But it also has to go into stretching the bonds, getting them farther apart as they heat, and some of it gets stored as rotational energy of the molecules zipping around, rotating around themselves, and that does not count as kinetic energy because it's not making them move faster from place to place. So now instead of having just stretching bonds, you're stretching bonds and rotational energy, stealing away from the energy you put in. So less of it goes to kinetic energy, less of it goes to temperature changes. So it's harder to heat water. I'll move to the next slide. Now I'm going to move to the next slide. So boiling. So during that process of boiling, of course, molecules are escaping the liquid, completely breaking the intermolecular forces. Well, to do this, the water molecules are still being attracted to each other as they break away. So as they break away, they stretch those bonds, and that stretching, that attraction between them, slows them down. So they're turning a good deal of their kinetic energy that they had as they left the liquid, that's being turned into chemical energy as it breaks away completely. Now, this is also a very sudden thing. Either you're part of the liquid or you're not part of the liquid. There's no in-between kind of partish of the liquid. It's either you're with them or you're not with them. So that process happens very suddenly. So all the energy you dump in during boiling is being converted into that chemical energy of fully stretching and breaking those bonds. Now, if that steam molecule there, that gas molecule of water, comes back to the liquid, it's going to be attracted and it's going to actually snap in and accelerate as it comes back closer and hit, converting that energy back into heat. But whenever they leave, they stretch those bonds and they turn it into chemical energy. So all the heat you put in during that process is turned into chemical energy, and its name is still enthalpy. Remember, enthalpy just means heat for now. And it's the enthalpy of vaporization for boiling. And that's because when water evaporates, it's called being vaporized, right? It's turned into a gas. Now, since the bonds are being fully broken instead of just stretched somewhat, it takes more energy to boil a sample of water than it does to melt the same sample of ice. It just takes more energy because at ice, you're just stretching the bonds. At the boiling point, you're actually breaking them and fully stretching them all the way out to broken. I apologize, that should be larger. So I'm going to move on to the next slide. If you need to pause, go ahead. All right, gases. We saw from our graph that gases are super easy to heat because they're such a steep curve. Their line is so steep, I should say. Now, the reason for this is gas molecules are far apart from each other, which means their intermolecular forces between them don't exist because they're already broken, those intermolecular forces. So as you heat gas, you don't have to stretch those bonds because they're already broken. So it's super easy. All the energy you put in basically gets turned into kinetic energy, speeding the molecules up. Now, a small part of that might be turned into rotational energy. But they're already rotating pretty quick already. So this idea that, yeah, so the stretching doesn't happen anymore, that's the key difference here. So almost all the heat you put in goes directly into kinetic energy. I'm going to go on to the next slide. If you need to pause, go ahead. So a quick recap here, right? So here is this not very steep part, And that's because this part, you're stretching bonds. So when you have water, you have to stretch bonds and dump in and give energy to rotational energy. And then the last bit of it goes into kinetic energy, which is what we see as a temperature change. So when you add energy to water, you have to stretch the bonds as they push farther apart from each other. Some of the energy gets turned into rotational energy of those molecules spinning around, and then the rest goes into kinetic energy. Now up here, you have no bonds to stretch. So when you put energy in, there's a little bit in rotational energy, but almost all of it goes right into kinetic energy, so they heat up really easily. And here, this is so long because we have to fully break the intermolecular forces. Those bonds between the water molecules are fully broken here. And here, they're just stretched. So you're just stretching the IMF. That's why it's less for the heat of fusion, enthalpy of fusion, than it is for the enthalpy of vaporization. And then down here, of course, we're primarily stretching the bonds. So it takes a good deal of energy, right? More than the gas does, but less than the liquid. All right, that's it. That's the big recap for today. I hope it got a lot out of that and you took some good notes. Have a good day, my friends.